Okay.
So,
Philip, all good on your side?
yeah, I'm good on my side.
Okay.
So.
Okay, awesome. Okay, so hi everybody. I'm Marco, and I work at Facebook as a production engineer in the server lifecycle space. And today I'm here with Philip from 9Elements. If you want to introduce yourself for whoever doesn't know you already.
Yeah, I'm Philip from 9Elements. We are an open source IBV. I probably already heard me in discussions. Yeah.
Okay, awesome. So today we want to discuss how opening the chain of trust all the way up to the root of trust actually can bring benefits not only for security, but also in terms of reliability and operations, especially when thinking about large-scale deployments. So we'll introduce the risks that come from deploying closed root of trust implementations and explain how those risks are actually exacerbated if you think of large-scale deployment. Then I think we'll all agree that the entry point to mitigate at least some of those risks is to switch to open source firmware. And Philip will take over and show the work that I have been doing on Converge bootguard and Intel TXT. So as a brief introduction, when we talk about root of trust, we basically refer to the set of hardware components and the software components that contribute to bootstrapping the chain of measurement and verification. So since this presentation is mostly focusing on Intel server-grade platforms, think of root of trust embedded into Intel ME or CPU, as we'll see with Converge bootguard. When working with closed root of trust, of course, we have a security problem. We don't have visibility in exactly how it works and the internal mechanisms. But there's also consequences for reliability and operations. Without considering actually large-scale deployment yet, if you want to support a root of trust, first and foremost, you need to have tooling for provisioning and testing. So you need to provision the platform, configure the TPM, for example, build the metadata for the firmware, and then you want a test suite that you can use to verify that the system is actually configured correctly. Ideally, you want to do functional tests, but you also want to do white box testing. So with understanding of the internal mechanism of the root of trust. Then, after building a tooling for provisioning, you also want to be able to do analysis of the failures. So validation will fail necessarily, and you need to actually be able to tell what is a failure that might constitute a security concern and what is instead a failure that has nothing to do with the security problem. If you start with this set of base requirements and you add a deployment at scale, you add a bit more complexity. First and foremost, reliability. You can think of some of the integrity flows like the RTM are very complex. It's a complex interaction between authenticated code module, system firmware, and later on kernel. And if you deploy at scale, necessarily you will start seeing very interesting way in which this can fail. And it becomes even more important to be able to remediate the systems. So send back to production immediately those that are not to be considered a security concern, and further investigate those that actually might be a security concern. Okay, so with this introduction, now we build on top of a closed root of trust, and this adds even more challenges. Development of tooling necessarily is much slower. You might have access to documentation which is not publicly available, but there's no open source reference implementation that you can look up if documentation is not clear or if you cannot validate a field of the metadata. And I think Philip has a very good example about that. White box testing cannot be done. You don't know exactly how it works internally, so you don't even know what exactly to do in terms of testing. And analyzing failures is challenging. Think of the core root of trust measurements. there's multiple contributions in the core root of trust measurements, and you wanted to know exactly what those contributions are, which section of the firmware they cover, and what is the impact of any of those contributions not matching what you expect them to be. So we all agree that to mitigate all these concerns, open system firmware is the necessary starting point. Now, OSF doesn't fix all the issues because the parts of the root of trust that are the closest with the hardware, for example, authenticated code module, are still closed, and they're very critical for having confidence on your root of trust. But this regardless of a very good property of OSF, which is that it tends to push openness even further in the stack. So you open up the firmware, but for example, think of the metadata for bootguard that probably Philip will talk about later. So the metadata is dependent on the layout of the firmware. So if you want to support OSF, you need to open up the specification of the metadata as well, so that you build open system firmware, but you can also regenerate the metadata. So this is a very good property of open system firmware. And despite not pushing openness all the way to the ACM, there's still great benefits. First and foremost, for example, being able to recalculate the PCR values or calculate them offline in a reproducible manner, and being able to do white box testing. So you remove the closed parts that constitute the firmware, and you already have much more visibility into what is actually being done by the ACM, for example, and what is actually a responsibility of the system firmware. And before, it was not even clear who was doing what. With this, I want to hand over to Philip, who will show their experience in enabling a converged bootguard in core boot.
Okay, thanks, Marco. So, so our solution to tackle the problem was using a platform integrated root of trust, which are part of the platform itself, and just use measurement technology based on that, basically trusted computing technology. And for that, we had to make the entire firmware stack transparent. This is not always possible. As Marco already said, you have some parts like the FSP and ACM and some other things which are not completely open, but we try to push code, or let's say push code out to the project we use, which probably re-implement things in open source, especially which are security and security critical parts. Also, with using open system firmware, we can find bugs easily and security issues in the SOC vendor stack. So it's always the case that there are bugs everywhere, right? So there's statistics about that, and that you at least have 0.5 bugs in 1,000 lines of code, as far as I know, even if they are programmed really well. So this is always the case. And for the data center, it's always really important to not have enforcing security available. So you can use, for example, a verified boot mechanism. But the problem with the verified boot mechanism is that the verified boot mechanism enforces security on the boot chain. And if something can boot anymore in a data center, and you have just one person of, I don't know, 10,000 servers, which is offline because there was a bug in the firmware, then this is a huge trouble, right? What we make use of is the Intel converged and security and trusted execution technology in our talk here. We also created open source tooling for easing the integration. We will talk about it now. Can you switch, Marco? Thank you. What is Intel TXT first? So Intel Trusted Execution Technology is the technology which protects the BIOS firmware from modification. So in our case, it's core boot firmware. There's some blob loaded in the beginning called Intel ACM blob, authenticated core module. It verifies the firmware itself. And then later on, there can be additional blob which is loaded for dynamic root of trust for measurement. That means we have some TE environment or TE-like environment later for running the operating system inside it or running virtual machines with it. This is the legacy implementation. Now, with Intel converged bootguard and TXT technology, both technologies are merged into one. That means that bootguard itself protects the early boot stage and the BIOS, and the Intel TXT allows us to do dynamic runtime measurements. Also, the TPM, which is used before in the legacy TXT implementation as root of trust, steps down, and Intel ME takes over. That means the Intel ME fuses are a new root of trust. This technology can also be combined with the Intel PFR, so the platform firmware resilience technology. That means you can also chain that together with another technology, FPGA, which verifies the firmware parts on the PCB. Yeah. Currently, open system firmware CBNT status is that first open source implementation, which is really open source because it also has an open source TXT driver, which is not available in UEFI yet. So UEFI has no open source CBNT implementation. It's based on the legacy TXT implementation we did for Coreboot some time ago. And we also implemented testing and tooling open source. So there's a security suite called Converged Security Suite available open source. We soon also plan to implement PFR support. For the Coreboot and CBNT implementation, we had to go through 3 steps. First steps was the BIOS packaging. That means we have to package the BIOS around with some firmware agnostic structures. They're called BPM and KM in order to have bootguard to verify it. And the second step, we set up everything in the TXT driver inside the open source firmware, so that the dynamic root of trust can be run from the operating system side. And the last step is the compliance verification with the test suite, because you have to fulfill multiple, let's say, tests in order to be able to run a dynamic root of trust for measurement. And the complete implementation is done on the OCP data lake platform. 2 days ago, we had success running the first system with it. So it's going to be released soon. Also, there's some stuff already out there in the open source projects. Yeah, the Converged Security Suite is an idea of us, of 9 elements. So it's a tool and tooling and test suites for inter-platform security technologies. It's BSD licensed. It has only Linux support at the moment, but probably we plan on Windows support as well. And it's available on GitHub. You can just check it out. It's there in order to replace existing NDA tooling. And it also offers an API if you want to integrate with different other programs. And the interesting part is it's completely firmware agnostic. So whatever firmware you use, if it's UEFI or Coreboot or Slim bootloader or whatever, Min platform, you can just use it. The tooling works on all firmware. Yeah, there are two things the firmware does. One thing is provisioning. So it provisions the platform so that you can use those kind of technologies. For example, for the old legacy TXT implementation, there's a tool which provisions the TPM with specific indexes and also can read out those properties and provision it with it. For bootguard, we have an additional tool which is not open yet. We are working to release that together with Intel. It handles the BPM and KM generation. So about the structures I already talked about, which was step 1. So these structures need to be generated. There's no open source tooling yet. And we can pass any type of firmware with it and also do cryptographic operations on that. That means we can sign, for example, the BPM and KM and generate it for a specific firmware. And yeah, the last step is testing. So testing is quite important if you want to verify if those complex security technologies really work on the platform. So we have a test plan yet for the legacy TXT implementation, which will soon be extended for CBNT as well, with 75 tests. That doesn't sound that much, but it's already covering a lot of stuff. So we're trying to improve it over the time. It already supports UEFI, TXT, T-boot, also integration tests and TXT ready tests. So these are quite useful. At the moment, it requires root access and defmem access, but probably will in the future write a kernel driver for that. And we have API support for that as well. And for the bootguard suite, which is planned, we will also later on provide a public test plan and try to cover the BPM and KM validation on the system. Probably much more, but we will figure that out. Yeah, and if you want to get in touch with that, you can just check out the information from Intel on CBNT. You can also look at the Corbu tree about the patches we posted so far, and you can also just do pull request at the Converge Security Suite or just use it. So give us feedback. We are happy to get feedback on that. Yeah, that's it. Thank you for listening.
So Philip and Christian, there are several questions. So this is the question from Davo. Is OCP looking into standardizing a set of root of trust to address closed root of trust problems? I think this was the comment, I think, Christian, you made about the closed root of trust, challenges with the closed, the binaries. I think the question is probably targeting that specific portion of your presentation.
Yeah, so let's say we found our own way. So we use platform security features, which are not really completely open, right? So for sure, you can probably in later run they plan to be open on some point, but that depends on Intel. It's always hard to rely on SOC vendor features. For sure, we could use different kinds of features, and the OCP could specify that. As far as I know from the security working group, there's no, so there are options you can use, but there are also recommendations, but there's no enforcement from the OCP side. And I also don't know, so this is probably something we should ask Elaine, if there is any work towards an open root of trust.
All right, I think there is another question from Paul. Will this interact with the PCIe component measurement and authentication, CMA?
Not yet, so I don't know. I need to look into that. So this is a specification, probably PCI Express specification is about security, also having similar web of trust technologies. We didn't look into that yet, so probably this will come up on some point. For sure, we're doing everything upstream to the community. So as soon we need to support it, we're probably going to do it, but not yet so far. Yeah.
Yeah, this may be more to do with the DICE compliance and device attestation protocol.
Yeah,
as well,
that is also
right?
Probably if you have more like this question, please also go to the security working group. It's probably tomorrow, right? And I totally forgot about the schedule, but they have also
Thursday.
a session.
Yeah, it's Thursday.
Okay, Thursday. Then please go ahead and I re-ask this question and give them feedback.
Yeah. Okay, so there was a question probably for the benefit of the rest of the folks. Is CRUD a technical term?
CRUD means create, replace, update, delete. Yeah, it's a technical term. Sorry for that. I just don't wanted to write it out completely. So it's about generating those structures and updating them, and yeah, replacing or
delete. Yeah.
Hey, Philip, this is
create,
Bill.
replace, delete. Yeah.
I just wanted to also address that question on security and root of trust. As you mentioned, the security group has authored a series of specifications or recommendations. It's a specification, but it kind of comes in the form of a recommendation. And they explain some of the key features and key attributes of establishing root of trust of the platform and attestation. It kind of goes in hand with what the OSF group is doing. Eventually, we want to make sure that platforms are implementing that their recommendations. We'll probably initially treat this as a checklist and ask platform providers to at least to go through the security specification and note what is implemented and what isn't implemented, because we think that this implementation will take time. And we hope that some of those implementations are open sourced and shared through the work that the OSF group is doing.
Yep, agreed. Let's see. Do we have any more questions? I think you covered pretty much all the questions. Thanks, Philip and Christian. Excellent update.
Thank you.
Thank you.